In this talk, I will present the result that were obtained together with Professor Mikhail Igorevich Kamensky and Professor Valery Vladimirovich Obuchovsky. During the last decades, the theory of fractional integral derivation has become one of the most popular and important areas of mathematical science. Numerous problems of science and technology described in terms of fractional differential equations and inclusions. The derivation and its applications are presented in the following monographs. Can you see on the slide? Are you see?
Yes, we can see. Second page now.
So, thank you. The fractional integral for the alpha of a function g is the function I alpha of the following form 1, where gamma is a gamma Euler Euler's gamma functions. Among them, the Caputo fractional derivative stands out as saves the fundamental properties of the ordinary derivative and has application in physics. Example, if we consider equation for the motion of a ball of a mass m and a radius a under the action of an external force F in a viscous medium, can the form 2, where W is a drag force given the formula 3. In the formula 3, we can see the integral part. This integral part can be is the Caputo fractional derivative. We can see on the slide the definition 2. Here is a definition of this fractional derivative. It is the function CD of the following form 4. It is form. Can be presented, can be as a part, the integral part of the 3 of the order alpha is equal to 1 or 2. Beginning in the second half of the 20th century, methods of nonlinear analysis extend into the theory of differential inclusions. The development of the theory of differential inclusions is connected with the fact that they are a convenient apparatus for the describing systems of in a control theory, mathematical physics, and mathematical economics, and elsewhere. Thus, the study of fractional differential inclusions turns out to be relevant in modern mathematics. Let us recall some information from the theories of measure of non-compactness and multi-valued maps. We denote by E is a Banach space and introduce the following notation, which can you see on the slide. Are you hear me now? It's please tell me, are you hear me?
Yes, Garik, I will let you know if something is wrong.
Thank you, thank you. And we consider the definition 3. Let A be a partially ordered set, then a function beta is called a measure of non-compactness in E, if for each set omega we say have the equal 5, here the values beta of the close of the convex hull of omega is equal to values beta of omega. As example of a real measure of non-compactness is the Hausdorff measure of non-compactness. It's infimum by epsilon less than 0, for which omega has a finite epsilon net in E. As other examples, consider the measure of non-compactness defining the space of continuous function with values in space E. Are the modules of fiber non-compactness. It's by the formula 7, and the module of equicontinuity, which can you see on the slide. So in the cone R2 plus, consider the measure of non-compactness nu, which it's a vector measure of non-compactness, where components, this vector measure of non-compactness is the modules of equicontinuity and the Fading modules of fiber non-compactness. Let X and Y be topological space. Let a multi-valued map F is said to be upper semi-continuous at the point X if for every open set is a subset Y such that image of X is subset V, there exists a neighborhood U of X such that the image of U is the subset of V. A multimap F is called condensing with respect to a measure non-compactness beta if for each bounded set omega, which is not relatively compact, we have the relations 10. And from theory of multivalued map, it's known the following theorem, fixed point theorem, theorem 1. Let M be a convex closed bounded subset of E, and M be a beta condensing multimap. Then the fixed point set of F, it has the point X belong to image of this point, is a non-empty compact set. We need also the following definition. For a given P, a multifunction G is called LP integrable if it admits LP Bochner integrable selection, and the LP integrable bounded if there exists a function C such that the norm of G in the point T less than or equal to Xi of T for almost everywhere T from the segment 0T. The set of all LP integrable selection, a multifunction G, is denoted by SGP. Now, let us consider the Cauchy problem for the semilinear fractional differential inclusions in a separable Banach space E of the following form 11 with initial data in the formula 12. Here, CD is a Caputo fractional derivative, F is a multi-valued maps, and A is a linear closed operator in E such that A is generating a uniformly bounded zero semigroup T. Denote by M as supremum norm this operator T in the point T. Let the multimap F be such that the conditions F1, F2, F3, F4 the condition F1 is written as for each fixed x, the corresponding multifunction f admits a measurable selection. F2, if we fixed the parameter t, the corresponding multimap f is upper semi-continuous. The condition F3 is a boundary condition. For each r, the existing function omega belongs to L infinity, such that for the x with norm less or equal r, we have the inequality 13. The condition F4, it's a regular condition in terms of measure of non-compactness. There exists a function mu such that for each bounded set Q, we have the inequality 14 with the Hausdorff measure of non-compactness in E. Then, for the continuous function x, consider the multifunction phi capital F such that the values of phi f is equal to our multimap f at the every point t. From above condition, it follows that the multifunction phi f is LP integrable for each p. And to solve our problem, we will use the superposition multi-operator PF infinity defined in the following formula. In this formula, the value of operator PF in the point x is a set of all L infinitive measurable selection of the multifunction phi f. And a mal solution of the Cauchy problem 11-12 on the interval 0 tau is called the function x, continuous function s, which can be represented as fighting. Here, the family of operator G and tau is not semi-groups, but this operator possesses the following properties. It's the linear and bounded operator, and these operators are strongly continuous. It's the conditions 1 and 2. To search for mal solution of our problem, consider the integral operator S, and then consider the multi-operator G given in the following way. This multi-operator G is a resolving multi-operator for our problems. It's clear that the function x is a mal solution of problem 11-12 on the interval 0a if and only if it's a fixed point of the multi-operator G. Then we prove the next theorem for the multi-operator G. The multi-operator G is a condensing with respect to measure of non-compactness nu, is a vector non-compactness nu. And this multi-operator is upper semi-continuous. And we can prove the local and global theorem of exist of mal solution of our problem. The idea of the proof of as follows. In the space of continuous functions, we take a closed ball of a large radius, and we show that the multi-operator will transform this ball into itself. Since the multi-operator is condensing with respect to the measure of non-compactness nu, then by theorem 1, it's fixed point theorem, this multi-operator G has a fixed point, which is the solution to our problem. Next, we prove a theorem about the continuous dependence of the set of solutions on the parameter and initial data. That is, we study the following problem, which can you see on the slide. We will need the topological properties of the solution set. For it, we need the following definition. A metric space X is called contractible if there exists a point x0 and a continuous map H such that the values of H from 0x is equal to x and the value of H in 1x is equal to 0 for all x from x capital. A compact metric space A is called in a delta set if there exists a decreasing sequence AAM sets of compact contractible sets such that A is equal to intersection of sets A n. We prove that the solution set, our Cauchy problem, is a delta set. This makes it possible to solve periodic and antiperiodic boundary value problems, which can you see on the slide. For it, we will consider the translation multi-operator PA along the trajectories of differential inclusions 11 defined as 24, where D is an open subset of E. Notice that PA may be represented in the form 25, where sigma is a multi-map and theta is a continuous map. And then we can prove the next theorem. Theorem exists of solutions of periodic of antiperiodic value boundary problems. But for it we will need that the semigroup will be exponential decreasing. This condition you can see on the slide. Then we can consider the following generalized boundary value problem in the separable Banach space E of the form by the formula 27, 28. The initial data 28 is a form of inclusion. Here, the multi-operator delta capital is a R delta multimap. Indeed, the values of this multi-operator data is a delta set for every for every continuous function x. The above boundary condition is fairly general and includes basic obvious cases of the periodic problem or antiperiodic problem or problems in the particular cases I or 2I or 3I. It's particular multi-point discrete mean condition, which can you see on the slide. We prove the next theorem, theorem 7, under conditions A, F1, F1, F4, if the k less than 1, then the problem 27, 28 has a solution. So by using this result, we can consider the approximation of solutions for the inclusions 27. These inclusions. For it, along with inclusion 27, for a given sequence of positive numbers Hn converging to 0, consider the following inclusion 30. Here, H is a semi-discretization parameter. Operators AH are closed linear operators in Banach spaces AH. And we suppose that the multi-maps FH satisfies conditions of type F1, F2, F3, and 4, and F4 for every H. We suppose that for each H there exist linear operators QH and PH such that QH on to QH is equal to identity operator, and QH on PHX converges to X as H converges to 0 for each X belong to the space E. And these operators are uniformly bounded by the formula 33. And initial data we can write in the form 34 and 35, which can you see on the slide, by using the operator QH, operator delta, and operator PH. We prove the theorem 8 that under condition 29, the sequence XHN is the sequence of initial data corresponding HN is relatively compact, and its limit points are initial values of solution to inclusion 27, 35 boundary value conditions 28. And we can consider also the controllability problem. The controllability problem by the formula 26 and 36 and 37. Here, the multimap F is satisfy condition F1, F4. The function xt is a prehistory of function x for the moment t, defined by the formula this you can see on the slide, and the control function u belongs to the space of L infinity, where u is a Banach space of controls and b is a linear bounded operator. So The controllability problem which we solve may be formulated in the following way. For a given initial function v and given y belong to E, we will consider the existence of mass solution X and control U such that x is equal to V on the segment minus H0 and the value of x in a point A is equal to y1. And under assumptions A, F1, F2, F4, suppose the condition F3 has the following form. Then controllability problem 36, 38 has a solution. It's thank you for your attention.